Can someone confirm if I'm audible? Give me a moment. Okay, so we can start now. So I'm Anand Singhal, a PhD student from IIT Jodhpur, and today we'll be doing the last live session of this course, Digital Electronic Circuit, which is taught by Professor Gautam Saab from IIT Kharagpur. And I'll be assisting you in solving some of the similar problems to week 12 assignment, which is the last assignment of this course. And also I'll be at the last of this lecture, I'll be telling you some of the important questions from all the weeks that we have covered, so that it can help you in your exams and all. And if you have any particular doubt, you can ask me at the last of this lecture. And uh, this will be the last lecture for this course from my side. So without further ado, let's start the. So here's a course outline. So we have covered each and every topic now for this particular course. In initial weeks, we completed the combinational part, and then we started doing the sequential circuit, which was the more important part as compared to the combinational one. And in the sequential circuit only, we have also completed the applications part. That is, we have also done the converters and all DAC, ADCs, etc. in the last week. And before that, we have already covered the state machines and all the flip-flops and counters, all types of counters, etc. And we'll be now ending this course with a more of an application or a theoretical topic, which is a memory organization. So we'll be studying some of the different types of memory in this particular lecture. That will be RAM, ROM, PROM, and some of the programmable gates such as PAL, PLA, etc. And then there is some FPGAs that we'll be studying about. So this lecture will be more of a theoretical lecture because we will have more theoretical topic and some of the numericals related to these particular memories. So let's start with the first problem. Okay, so the first problem states that each cell of a static SRAM contains. So first of all, static is itself S, so there will not be an S. So static, there are two types of RAM. RAM is random access memory, which is volatile. That is, it is not permanent. I guess you all might be aware it is all in our computers also or our laptops. We all have this uh, RAM. We often buy our computers by seeing what amount of RAM it has. It has a 16 GB RAM, etc. So we have two types of RAM. One is static and one is dynamic. So basically, the most basic structure of SRAM is known as 60 SRAM, which is also 6 transistor SRAM. So, so for the answer, for the sake of answer, the answers would be 6 MOS transistors can make an any SRAM. But for the sake of explanation, I have like added the circuit of this particular SRAM, and I'll be going through a very in a very brief manner. I'll be going through this circuit and how SRAM can work. So this is an SRAM in which we have 6 transistors. You can see we have transistors M1, M2, we have transistor M2, M3, M4, and then we have transistor M5, M6. So these are the transistors that we have. Now you can clearly see if I highlight one of the transistor with the red color. So this is a PMOS and this is a NMOS, and they are connected together with a single input, and they have a particular output. So this circuit is nothing but a CMOS inverter, which we have already covered a lot before also. So this is a CMOS inverter in which we have, let's say, a V in, we have a V out, and we have a VDD here, and we have a ground here. So this is nothing but a CMOS inverter. This M3, M4. Similarly, we have M1, M2 also as a CMOS inverter. So M1, M2 and M3, M4 are four transistors, which are basically two CMOS inverters. And then what we have is we have the input of M1 M2 is connected to the output of M3 M4. So basically, let's say this is M1 M2. So the output is connected to the input of M3 M4, and the input of M3 M4 is connected, and the output of M3 M4, which is this, is connected to the input of M1 M2. So this is nothing but a cross coupled inverters. We have already studied. This is the most basic circuit of a memory, which is presented here, which are cross coupled inverters. So how it can act as a memory? Let's say if I apply any input 1 here, so the inversion will be 0, and then again it will be inverted and 0 will be 1. So it will always store this 1 once I apply any input. So this is how it is known as a memory. So now this particular RM, it has a word line. You can see it has a bit line, complement and bit line. So I'll be telling more about. So a basic RM has three types of operations. One is a read operation, second is a write operation, and one is a hold operation. So I'll be telling in very brief how hold operation works initially. So let's say we have this circuit. Yeah. So for hold operation, what we have is, so for hold operation, what we have is, we have both, we have our word line, that is this VDD. We have this as ground. So once we have this ground, so you can see if we have this gate voltage, which is the transistor M5 and M6. So if we have a zero gate voltage, what will happen? These both transistors will be in cutoff because there is no voltage applied to conduct the electricity. So once they are in cutoff, so we are having just this particular circuit, which is I am denoting in dots, and this circuit is nothing but this. So whatever input it has been before, it is just holding that particular input. So that is why we call it as the hold state. So this is the first state in which we have the hold state. Now I'll talk about the second, which is a read state. So what do we have in read state? We have see, you can let me first summarize. So we had this M1 M2 is one of the inverter, then M3 M4 was one of the inverter set, then this M5 M6, they are called as access transistors, using which we can access our RM. And then lastly this Q and Q complement, which have the input and output of these two particular cross inverters. They are also known as storage nodes. So this is the point where the storage happens. So what happens in the read? So what I can do is I can make a very simplified circuit. In between I have these cross coupled inverters, then I have this M5, then I have this M6 here, and these are connected to the word line, and these both are connected to bit line. One is bit line complement and one is bit line. So what we do in read operation, we make the WL as VDD, that is very high voltage, and we pre-charge, basically we pre-charge BL complement and BL at VDD. So now what will happen? So I'll go again in very brief. So we have applied a VDD here, and if you pre-charge, so we have also have a VDD here. So if you pre-charge this BL to VDD, what will happen is this transistor will conduct and this transistor will also conduct if we pre-charge. So once we have a high voltage here, what will happen? This particular uh, once we have a high voltage here, the input of this will become low, and once we have a low voltage here, the output. Sorry. So since this is low, so this also becomes high. So this is how what we are doing. So this is the basic operation, and what is happening here? We are just reading the bit. So once it's conduct, so whatever will be the Q, we will read that. So that is why we call it as a read operation. And just to write anything inside the MOSFET, what we do is, sorry, inside the RAM, what we do is we make, which is the third operation, write operation. We make VDD and we just give BL the VDD. So what we have is, let's say we have a voltage here, we have a VDD here. So what will happen? This will be now get to a high value, this particular node, because we have a particular drain voltage and we have a particular gate voltage to make the transistor turn on. So once we have this, we have our WL as VDD, we have, let's say, our BL complement as VDD. So if we let Q as 1, which is one of the storage node, so if Q is 1, you can clearly see which is the input. So the output of this particular MOSFET Q complement will become 0, because it is of nothing but an inverter. And if we have, let's say, now BL is grounded, since BL complement is BDD, so BL will be grounded. So what will happen is, when BL is grounded and when this Q is 1, so now what will happen, this becomes the drain of that MOSFET and this starts charging. So what will happen, there is a flipping. So from Q0, the states goes to Q as 1. So the right operation is also known as flip operation, or flip the states. So this is all have been covered in the theoretical lectures also. So for more information, you can visit there. But I'm just giving a very basic overview just to tell you that what are the things that you need to know to make that you should know the basic working of an SRAM. So we can make an SRAM using 6 MOS transistors by this. And the most basic thing is we have 3 operations, that is read, write, and hold. And read we have word line as 0 and read line and BL also as 0, so that we are left with this circuit, and this circuit holds whatever state it was been previously before. Then we have the read state, in which we had this WLS VDD, and both BL and BL complement are pre-charged to VDD, and this again reads the operation whatever is there in the storage nodes. And to write anything, we give the high supply voltage to both word line and bit line, and whatever is the input state, it will write it. So let's say if we want to write Q as 1, so what we did is Q complement became 0, and similarly now once we applied the voltage high here, this Q will become 1. So this is how there is a flipping of state. So if it has stored 0 before, it will store 1 now. So this is how it is also known as the write operation. So the correct option for this answer would be option A. So if you have further doubts in this problem, you can ask in the chat box. Otherwise, we can move forward because it is completely theoretical again. Is there any doubt? Okay, the right operation you're asking. Fine. So let me take a quick example. So let's say if we have Q as 1, and once we give this VDD and VDD here, which is the operation for write, so it will become high. This Q complement node will become high. And what is the objective? We want to write, let's say, 0 in Q, which is a storage node. So once this node will become high, what will happen? The input of this transistor, that is this CMOS inverter M4 M5, will become high, that is, let's say, 1. And the once we have this input as high, our output, that is Q, will become from 1 to 0. So if it has been storing 1 before, it has flipped to 0. So this is the case for this. I have explained the second case. So now what has happened, that we have written 0 here. So to write 0, what we have done, we have done the word line as VDD, and also bit line as VDD, sorry, bit line complement as VDD. So once we have this 0, this is how it is written. So similarly, if we wanted to write 1, then we need to give now the bit line. So we can write 1 from this side now. So let's say if we have a 0 here and if we have a VDD here, so what will happen, it will not conduct, it will still remain in the 0 state. That will make Q complement high. So now the Q complement, that is 1, will be stored in the left state. So this is how it can store whatever you want to in this circuit. Is it fine? Okay, so maybe we can move forward now. Now it says the minimum number of transistors required to make a dynamic RAM, that is a DRAM. So again, DRAM is of two types. One is 3T DRAM, that is 3 transistor DRAM, and one is 1T 1C DRAM. These all are, I guess, covered in the lectures also. So we can make a DRAM using one transistor. It looks something like this. So again, we have, let's say, a VDD, a VIN, and a one capacitor if we have. So this is our DRAM. So we can make a DRAM using only one transistor and one capacitor. So the answer would be 1. Again, the basic explanation I'll give out for these two circuits, which is similar to the previous explanation. So these are the two types of DRAM that I have already showed. So again, DRAM has both read and write operation. So for read operation, let's say what we have is we have this is the bit line. So we have this as 1. So once we have this one, so this will be VDD, and so once this will be VDD, and let's say this will be VDD. So what will happen? This particular charge will get stored here. So it was VDD here, and it will be VDD here. And once we have a VDD here, it will store. So this particular circuit, which is I'm again making with a dotted line, is acting as an inverter. So if we have an input X, it will give out a X complement here. So once we have this VDD as an input, this MOSFET will start conducting and all the charge will get stored here. So this is how we are writing or storing 1. So we have stored 1, and once we have given a high input here, it will be low here. That will make the BL2 low. So this is how 1 is stored. And similarly, now if we give a 0 input here, let's say if I use a different thing. So what will happen? We have this stored VDD here, and this will come out here. So now the charging happens in the opposite direction, and this node will become 0. And once this will become 0, this X complement will become high. So this is how we are storing 0. So storing is happening in this capacitor in this circuit. So this is how this particular circuit 3T DRAM works, and similar operation stands for this 1T 1C. So we have this word and bit line. So once this both of them will be 1. So what will happen? This will get stored here VDD VDD, and once we have this 0, this discharge again, and this becomes VDD, and this becomes 0. So initially it was plus VDD, and then it was 0 volts. So this is how we are reading and writing 1, and this is how we are writing and reading 0. This is the very basic operation of a DRAM. So answer for this particular question will be 1. So still, if you have any doubts, you can type in the chat box. I'll explain again. Is it clear to everyone? Please type in the chat box if it is clear so that we can move forward quickly. Shall I proceed? Okay, fine. Okay, so we have now a type of a numerical but a very simple problem. So we have, again, we need to have a theoretical understanding. So this is a circuit which is explained in the theoretical lectures also. So we have this CSRW circuit in which we again do this reading and writing operation, and we have a confined truth table for it to solve these problems. So we have the inputs as CS complement and R by W complement, and it has WR and read. So WR is write. So this is a truth table for this particular circuit. We have 4 possible combinations. So whenever both control state and read by write are 0, so what happens? It starts the writing state, and when this is 0 and this is 1, it starts the read state, and this does not work here. It is just holding. So this is a particular truth table that will be very that will make uh, to solve this particular question very easily. So now the question says, in the given circuit, if the control logic input CS complement is 1, that will make CS as 0, and read by write complement is 1. So what is the condition given? That CS is 0 and read by write complement is 1. So we can easily check in the truth table. The following consider condition corresponds to the the read operation. So what will happen? Which operation will take place? It will happen. It will be in the read state. So you just need to learn this truth table for this particular question, and you will get the answer quickly. So I hope it is clear, because it is again more of a theoretical part. So let's move forward now. If it is not clear, you can type in the chat box also. So now it is a numerical question. So it says how many data inputs and address input lines. So there are two things that has been asked are required for a 128K cross 16 memory. So for any memory, we have a particular representation, that is 2 raised per p times n memory unit. And we have certain terms such as data input, which is asked. Then we have address input lines. So which is denoted by p here. Then we have n, which is the data inputs. Then we have m, which is the number of locations. And it is nothing. So number of locations times data input is equivalent to this given information, that is 128K cross 16 memories, and we can easily compare. So this is nothing but p is the number of address lines. So 2 raised per p is equivalent to 128K. 2 raised per p is 128 is 2 raised per 7, and this kilobyte is 2 raised per 10 bytes. So 1K is 1024B. I hope you are already aware. So which is nothing but, sorry, 2 raised per 10 bytes. So we can easily write 2 raised per p is equals to 7 plus 10, which is making p as 17. And again, it is given that this m cross n is 128 cross 16. So what we'll do now, we need to find what the number of data inputs, which is nothing but n. So we'll calculate the n here. So this is again 128K cross n. So I'm writing it here now, is equivalent to 128K cross 16. So that will clearly make this n as 16. So this is the data input lines, which is 16, and this is the address input lines, which is 17. So the correct answer will be option D. Is it clear? Please confirm it if it is clear. You can try out this question. We can start in 2 minutes, and please confirm it if the last question is clear in the chat box. So we have this problem in which we have 1 mega cross 4 memory. How many 1 mega cross sorry, we need to construct this 1 mega cross 4 memory, and we need to find how many number of 64 kilo cross 4 memory circuits are required. So this is a similar problem as we have already done for a, let's say, a multiplexer. So what we'll do is to make this 1 mega cross 4 memory, how many 64 kilo cross 4 memories are required. So we need to divide it. So what we have is for 1 mega, so we have one answer 16, so we'll check. So for 1 mega, it is nothing but 2 raised power 10 kilo, because it is 1 mega is 10 raised power 6 kilo. So what we'll do is 2 raised power 10 cross kilo cross 4 and 64 cross k cross 4, and again 2 raised power 10, sorry, this kilo and 4 will cancel, and 64 is again 2 raised power 6, so it will give out to be 2 raised power 4, that is 16. So what we can write is 16 64 cross, sorry, 64k cross 4 memory is required to build a 1 mega cross 4 memory. So the correct answer will be 16 here. Yeah, so it is correct. So I hope it is clear, so we can move forward now. So now this is a question of PLA, which is a programmable logic array in which we have both AND and OR gates as programmable. So I guess inputs are not visible clearly, so I'll make them. Maybe you can try it out and let me know the answer. Otherwise, I'll solve it out. So I'm combining the inputs and the given outputs so that it is easier for you. So this is what we have, and we need to find F1 and F2. You can try it out in 2 3 minutes. Otherwise, I'll start solving it. Okay, so we have this programmable logic array here. We will just write each of the inputs and outputs, and to solve it, we'll apply the K-map technique. So first of all, we'll write these inputs and outputs. So this is A complement, as you can see. This is A, this is B complement, this is B, this is C complement, and this is C. So what we have as the output of 1, so I'm writing 1 2 3 4 here. Output of 1 will be this is C complement is getting ended with A complement. And for B, we have C, B complement, and A. Then for 3, we have C complement and B complement. And for 4, we have C and A. I hope it is clear. Is it clear? Please confirm right now. So this is B not B complement. Is this step clear? Okay. So now we have the OR gates. So now I'll write the 1 and 2 of OR gates here. Sorry. So it is 2 plus 4. So it is A, B, C plus AC. And then we have 1. Sorry, so this was 2. And then we have 1. So you kept the connection button time. Which connection you are telling about? Can you elaborate? So they were given, actually they were not visible. So let me try to show you. If I zoom this picture out, can you see the small cross? Yeah, so they were given, so they were not visible in light. So that is why I made them like that. So for 1, we have 1 plus 2 plus 3. So it will be A complement C complement plus ABC plus B complement C complement. So now we have this f1 and f2. So for that we'll solve out what is f1 and f2 given. So f2 is given as 1 XOR 1, which is VDD. So this is 1 now and this is 0, and 1 is getting XORed with, sorry, for this 0 is getting XORed with 1, and 1 is the output. So 1 is what, this A complement C complement plus ABC plus B complement C, and F1 is 1 XOR 2, and 2 is this ABC plus AC. So first of all, we need to know that for any XOR gate, if we have a 1 and let's say an X input, so X XOR 1 is always X complement, and if we have a 0 and again X, so X complement 1 0 is X. So it is acting as a buffer if we have a 0 input, and it is acting as a inverter if we have 1 input. I hope it is clear, and we'll simplify these equations also before solving it. So F1 will be, so first of all, this AB, this 2, it is AC I'm taking common. Then I have A plus, sorry, B plus 1, that will give me finally AC. So 2 is AC, so I'm writing AC here, and we can keep that as is. So for F1 we have AC, right? Or it is at F2. So F1 will be, since we have a 1, so it will be inverter, so we will have A complement plus C complement. So I hope it is clear. For F2, it is a buffer, so we'll keep the same expression, A complement C complement plus B complement C. So we can quickly make a K map and write all the terms that are required. So for F2, so for F1 we can easily write the K map, or we don't even need to write that, because let's say we have A first and then B, C. So wherever there is C complement there will be 1, wherever there will be A complement there is 1. So we have these 6 terms related, which are 0 1 2 3 4 5 6 7. So F1 will be summation 0 1 2 3 and 4 and 6. Similarly, we'll can find it for F1, which is this, sorry, we can find it for F2, which is this expression. So I'm again making it quickly. Or ABC 7, we no. Okay, so we can do it, I guess that will be quicker. We have ABC, which is ABC, so this will be 1. Then we have A complement C complement, so A complement C complement is here and here. Then we have B complement C, E complement C is here. So we have these terms. So what is this? F2. So F2 will be, now I'm writing it again, 0 1 2 3 4 5 6 7. So F2 is nothing but 0 1 2 5 7. We check the options. So F1 was 0 1 2 3 4 6, 0 1 2 3 4 6, which is this, and F2 is 2 0 2 4 7. 0 2 4 7. Okay, I guess I made a mistake somewhere. So ABC is 7, A complement C complement. So these, and the third term is B complement C. Okay, this is, have I written it correctly? Okay, so let me do a quick check. So ABC was 7, then I'm writing for other terms, so all the numbers. So this is A complement C complement. So there will be B here, there will be complement here, and the third term is A complement. This is B complement C, B complement C. So we have 7, we have this 0 1 0, which is 2, We have this 000 which is 0. We have this 101 which is 5, and we have this 001 which is 1. 01257. This is what we have. Did I write any expression? 0247. Let me recheck. 2. Let me quickly recheck. Oh, this was B complement, C complement. Okay, okay. So this was a complement. That is why no option was matching. So this was complement. I did not check it earlier. So A complement, C complement was this, and B complement, C complement was this. So I'm writing it again now. So it is ABC, which is his. Then we have A complement, C complement, which is this, and we have B complement, C complement. So these are the four terms that we are having. So 0247. I hope it is clear. Is it clear, everyone? So then I guess option A is matching now. Yeah. So option A is the correct answer. Is it clear, everyone? Please confirm it if it is clear. Please type in the chat box quickly. Okay, so we can move forward now. So again, it is one more theoretical question. So it is asking which of the statements is or are true. So the first statement says the main memory of a computer system must be non-volatile. So it is wrong. So RAM is the main memory of any computer, and it is volatile, as I've explained you in the previous in the first part of the lecture. The data memory can be built in using either ROM or RAM. So it is again wrong. It can be built by using both RAM and ROM. It is not that only one can build that. Again, the third option is write enable time is a time to be allowed between placement and available. So it is again wrong. Write enable time is the minimum time required to write any bit. So it is not the time between the placement. The last option is SRAM using CMOS using cross coupled inverters for basic. Yes. So this is the first question that we did, in which we made an SRAM using cross coupled inverters with extra transistors. This is how SRAM works. So option 4 is correct, which makes option D is the correct answer. Is it clear? This was a straightforward question. So I hope it is clear. I'm quickly moving forward now. So now we have a linear addressing in a memory IC. This IC has 1024 cross 4 bits. We are redesigning the IC from to have matrix addressing. So we have two types of addressing. One is linear and one is matrix addressing. So for linear, let's do it here. For linear, we have number of inputs to the address decoder that is asked. It is given by a certain formula. So I'm writing that, which is log 2m, and m is again this 2 raised power p times n was the term. So this is again 2 raised power p. So log to the base 2 1024, which is log to the base 2 2 raised power 10, and that will give us 10. Log to the base 2 2. So this is 1. So the final answer will be 10. So for linear, it is number of input to address recorders are 10. And for matrix addressing, we have again the number of inputs to the address decoder are the total by 2. So we have we have what we are getting from the linear times half, and the column address decoders, sorry, the column address decoder is equals to, so we for matrix we have certain rows and columns. So whatever rows we will be having, we need to have certain columns also. So we will again have a 5, so total will be again 5 plus 5, that is again 10. So in short, what we can write is for address for linear whatever we have got, it will be similar to that for matrix. So the answer will be 10, and this is again 10. So option D is the correct answer. Is it clear? Okay, we'll do it for two. So 2 or 4 8, we will have one more. So we will have a 11 here, and again we will have, so for 11 it will be 5.5. So 5.5 means we will require 6, and similarly 6 plus 6 will give you a 12 here. Yeah. So let's move forward. Again, it is one of the theories that has been covered. So we have two ICs in the course, which is IC2114 and IC2115. So I'll give some quick information. So IC2114 is a word organized IC which has common IO pins. IO means input memory types. Then again we have IC2115, which is bit organized, and it has separate memory. So now the question says, suppose you need to choose a suitable memory IC, either 2114 or 2116. Your requirement is word organized. So for word organized, we clearly need 2114 separate IO memory, and for this we need 2115 also. So we need both ICs first of all. So which of the above two memories are suitable? So only IC will not work, and only IC will not work. And since both are suitable, can only be the option if they will be a single IC. So for this particular question, none of them will be suitable because we don't have any single IC which can do this both operations together. So I hope it is clear. It sounds a bit confusing that it is asking which of the two memories are suitable. So which of the two means either IC 2114 will be suitable or 2115, but we will require IC 2114 for word part, and we will require separate IO pins from IC 2115. So we need both the ICs to work together to make them work in like that. So that is why none of them are suitable. Is it clear? The previous question is what kind of bits you are asking. In this question you are saying. So for this particular formula will be taught in the theoretical lectures also, I understand. So if we have 8 bits, then I guess it will work differently, because in this it is given what 4 bits. for linear, we are not even related to this, so even 8 will not affect this answer. But for matrix, I guess it might affect because we have different number of bits. But for linearity, it will be remain the same because 1024 will require the 10 address lines that is ours, the address decoders. It is in linear, and in matrix we will have a crossbar array. So that will also not affect the answer, yes, because so we can move further quickly. So you can try this out. I have already explained this in the first part, that is DRAM. So the question says we have a 3D DRAM in which you need to first write a single binary digit 1. So what we need to write? We need to write 1, then read the binary terminal, and we need to read it at y. So we need to find y. We need to write 1. So basically we need to have d in as 1. For this operation, what will be the correct value of w, r and y? So all of this is given. So w is this, r is this, and y is this. So you need to find the correct values of w, r and y to have the answer. So our values can either be 1 or 0. So you can let me know all the values. You can write the combination of w, r and y like 0, 1, 0 or whatever you are getting in the chat box quickly, and then we'll solve it. So I have already have the answer as 110. So we need to write 1. So first of all, if we need to write, so we need to make this w line as 1. So once we have both of them as 1, so this will make this v as high, and this is like an inverter, so y will be 0. And to make it read also, we need to have it 1. So w will be 1, read will be 1, and output will be 0. So the answer will be 110. That is already given in chat box. Yeah. So 110 will be the answer. So let's quickly move forward now. So again we have a similar question. So you can try it out and I'll solve in 2 minutes. Let me know the answer. What one answer is 4. So let me also try. So now we have two ICs here, IC2114 with, and one is 70201. So we have this as 1024 cross 4 bits memory, and we have this as 256 cross only 1 bit memory. So what is ours using both? How many ICs? 70401. So we have already done this. This is DEC0808, which is already covered, which is a kind of a 8-bit IC. So we have these three ICs. So in this it is asked 74201. How many are required for IC 21104? So we'll again go with 1024 is nothing but 2 raised per 10, and 256 is again 2 raised per 8. Yeah. So we have a 4-bit here and we have a single bit here. So we need to be careful about it. So the answer will be here, not the answer. So we require 7 IC 74204 to have. So since we have this as a single bit, so what we'll have to cover 4 bits, we'll either require 4 of them individually. so that it can cover 4 bits. So what I'm trying to say here is for IC 74201 can have a single IC 2114 cross 1 bit memory. But in the question it is given, so they have cleverly changed the 4 bits. So what we will have for each of this, we will require 4 more ICs. So the total 74201 required are 4 times 4, that is 16. The answer will be C. Is that clear? Does it make sense to everyone? Okay. So again, the next question is theoretical. So let me do it out. So it says EEPROM use ultraviolet lights through quad. So this is wrong. EEPROM is electrical ROM and EPROM is UV ROM. So this statement is wrong. In PLA, and array is fixed and OR array is so this is again wrong. PLA we have already covered. Both are programmable. In PAL, OR array is fixed. So in PAL is programmable array logic. In this OR is fixed and N is programmed. So this is correct. This is already covered. So DM has a higher packing density than, so this is also correct. This is theoretical. So 3 and 4 are correct here. I hope it is clear. It is a straightforward question, theoretical, so that I am not wasting much time on them. Now it says which of the following statement is true. In a RAM, the access time depends upon the location of the word. This is wrong. In sequential access, the access time is independent, so it is not independent. Same for location. Wrong. Independent, yeah. So it is independent. This is theoretical, so I'm not going much into that. So in RAM, there is a term access time which is independent upon the location, but it is dependent upon the value of that word, not the location. So I'm again quickly moving forward. This is nothing. Okay, so we have again a theoretical part. So SRAM offers. So first of all, SRAM offers very high speed, but it is high power consumption. Since it is static, so there will be static power consumption, which is more as compared to any DRAM, and it is expensive because of more number of transistors required. And then we have a lesser density from DRAM. So now question says high density, this is wrong. Lower cost, this is also wrong because it is expensive. High speed, it is correct. Lower power consumption is also wrong. So option C is the correct answer. So I hope it is clear. You can try this question out and I'll give the answer in 2 minutes. Yeah, sorry for the delay. So what we have, I guess I've got some answers. 10 is one answer. So we have this 1024 cross 64 specified number of word times the number of bits. So how many address lines are needed? So it is again similar to 2 raised per k cross, let's say n, where 2 raised per k is the number of words. And then we have n as the number of bits or words. And we have this k, which is the number of address, right? Which is, I guess, asked in the questions. So if we can compare 2 raised per k cross n, we have 2 raised per k as 1024, and k will be this is equals to 2 raised per 10. So that will make number of address lines is 10. So option C will be the correct answer, which is also given in the chat box. Yeah. So I hope it is clear. It is again similar. So maybe you can now try this question out. I hope the dots are visible here clearly. So you can take 2 minutes and let me give the answer quickly so that we can move forward. Any answer? Try to do it quickly. It is very easy. I hope you are trying the same. Please confirm in the chat box if you are trying the same, and please let me know the answer whatever you get. So I've got one answer as C. So others also please try and I'll solve it in 1 minute. So let me solve it then. This is very easy. This is A complement, this is A. This is B complement, this is B, and this is C complement, this is C. Let's say this is 1, 2, 3, 4. So for AND, 1 will be B complement, C complement. 2 will be 0 because it is B complement times B. 3 will be B C complement, and 4 will be, sorry, 3 will be these three. So A complement is also there, and 4 will be A, B, and C. Oh, I have written it wrong. I've written it. First is B complement C. Yeah, so first is B complement C. Now let's say this is 1, 2, 3. So for OR we have first as 1 plus 3, so which is B complement C complement plus A complement B C complement. 2 as 2 plus 4, so 2 is 0, so 4 we have ABC. But 3 we have 1 plus 2 plus 4. So this is B complement C complement plus ABC. So 1 is F3, 2 is F2, and 3 is F1. So F1 is ABC plus B complement C complement, which is ABC. So this is two options. We have ABC as F2 and F3 is A complement B C complement plus B complement C complement. This is the option. Yeah. So option B is the correct answer. I don't know why it took so much time. This is very easy to do. Okay, why are you saying C? Let me. Have I done something wrong? Why it should be C? Two answers I've got is C, I guess. So what is the difference between C and so F1 is different. So F1 is 3 and 3 is 1 plus 4. 1 plus 4. So 1 is plus 4. 4 is C comp C. This is C. 1 C B A complement. A complement B C. Yeah, so it will be B. Uh, why you are saying C? Is it clear now? I'm getting again S B. Please confirm if it is clear so that we can move forward. Yeah, okay. Okay, so like these are the some types of problem that can be covered using memories because memories is again very easy topic and more theoretical. So I guess a lot will not come in the exam from this. I'm not sure, but yeah. So now what we'll do is we'll discuss some of the very important problems from the previous weeks also, and you can go through it once and if you have any doubt you can ask again, and I'll just let you know the questions. I'll not solve them again, but what I feel is as important I'll let you know, and if you have further doubts you can ask. So I'll go from week to week. So from previous week, so I'll first start from week 11. So in week 11 we have done a lot of questions for ADC and DACs, and the most important is the SAR type ADC, in which we did, if you remember, if you attended my lectures, then we have done two types of question, which one was end of third clock and one question said that start of fifth clock, something like that. So they can play with these words just, and they will give you a long type of questions and you need to solve it. So this is one of the very important concept in which we covered. Then again, we in the SAR we had more ADCs such as Flash. So in Flash they generally give it for comparators, in which they ask the number of comparators, which is 2 raised per n. Then we have so this was the concept for ADC. Similarly, we have DACs in which we read more basically two ADCs which are R2R ladder and one is binary weight. The basic difference was between the output voltage. One was V divided by 2 raised per n. So this is nothing but VFSR times V in, and one was 2 raised per n minus 1. So these are the very basic concept that you should know. So in SAR, this is the most important question that I feel, in which they can play with this and starting or after the pulse and something like that, and they can ask you some of the most some of the outputs that can come out of this SAR ADC. Then we have Flash ADC. Then we have two DACs that I've already discussed, that are R2R and binary. So you need to be aware of these concepts. Then we have one similar question was there, so we are required to design. So is this assignment problem that you have written here? And the deadline has gone or it is still there? What is the deadline to submit this? Oh, so tomorrow. So I cannot solve it. You can ask later then. That will be unethical if I directly give you the assignment solutions. So I have already told you a lot of similar problems. So if you are able to understand them, then this problem is again very easy. It has been written 512K by 2K, and we have 8 RAM chips and 16. So I can give you a hint. So 512 by 2 will be the total number of chips, and 8 RAM chips will give a single. So for 16 you need to double them. So again, you have been provided with 2 cross-port decoders with enable lines. What is the minimum number of such decoders? And then you need to apply the concept for decoders directly. This is easy, so I cannot tell you the answer directly, but just be clear with your concepts. We have done a similar question today only. Yeah. So again, I was telling about some of the important problems from the previous week. So again, in week 11 only, we have covered this DAC problem, in which this resolution is some percent of full scale voltage. Let's say it was some percent of full scale voltage, and we know the full scale voltage is nothing but VFSR by 2 raised per n minus 1s. So it is this is nothing but resolution. So we can equate them and do certain questions, and we can find the number of bits here. So this was one more question that you need to have good grasp on, because this is again an important problem. This all will basically show that how much conceptual that you have gone inside the subject, and how clear are your concepts. So just don't uh, do the ratification, but instead try to understand the topic and understand all the concepts. Then in week, I guess in week 10, we did certain problems in which we had the state tables and we did the row elimination method. I'm not sure which week it was, but we had this row elimination method in which we need to find the equivalent classes. So this was again one of the more important topics. Then we had, in this particular lecture only, we had the state transition diagrams. You need to be aware. Even we had the state transition table, in which we have we start with this current state, present state, we have inputs, then we have next state, we have output. So you need to know how to make this state transition table, so that, or you can also call it a state table. So if you're not aware of these concepts, then you might not be able to solve a lot of questions. Then we again, in state table, we had these two types of models, which are Mealy and Murray model, if you're aware. So you need to be clear with all of these concepts from this particular lecture, which is a state transition lecture. Then we again, the state transition diagrams. So there were questions in which the state transition diagrams were given, and they were asked you to specify or find out certain types of functions, such as in this problem they are saying that uh, what will be the state of flip-flop? So there are four states, so that is why two flip-flops are required, and they are just asking for the flip-flop inputs. So what will be D and what will be DB? So this is again a very simple question. So if you know how to make a state table from a state diagram, then it will be done in like 2 minutes. This is very easy problem. So again, from week 10, you should be clear with the different types of method. There are, I guess, hazards also or not, I am not sure. Then you should know that how to make a state transition diagram from the table or how to make a state table from the transition diagram. So these are the very important concept that you need to know. Then I guess in the previous weeks that the counters that were very important. So we had asynchronous counters, we have synchronous counters. There was this particular problem which make the use of reset pin. So you should be aware of these also. So what is the basic difference? So asynchronous, what we have different clocks at different time. And asynchronous, we have a single clock and all the flip-flops are getting used at the same clock instant. So this is the basic difference between synchronous and asynchronous circuits. Then we had a very important counter named Johnson counter. I also ask you to read all of this and remember this 0 1. I guess there is a particular 3-bit Johnson counter which follows a certain pattern, and I ask you to remember all of these because that will help you in solving. So Johnson counter is nothing but a combination of D, and the last complement is connected to the input of first. So this is nothing but a Johnson counter. And for these types of counter, we have two n states. So let's say there are n flip-flops, so there will be two n states for these types of counter. So if you have 3 bits, if we have three flip-flop, we will have 6 states. If we have four, then we will have 8 states and so on. So you just need to memorize all of these things and you need to be clear with all of these concepts. Then this is again a similar problem. So uh, there are some counters given and you need to solve the single logic diagram or what are the logic circuits. Then we have yeah, so these are now the registers part. So we had, if you remember, so we had this one x0 x1 x2. We have the linear feedback register in which we did some of the XOR of certain two nodes and which is connected to this, and we just do the polynomial representation whatever is given as 1. So we do the XOR and connect to the 1, and we need to know the pseudo random sequences and all. So these is one single type of question, I guess, in this particular lecture. I guess this is week 7 or 8, I'm not sure. Then we had different types of registers also. We had serial input, serial output, serial input, parallel out. Then we have PI, PO, PISO. The most generic one is the serial input, parallel output, because it can make you solve the questions easily also, and this is interesting and more easy to solve. So you should be able to solve these type of problem, like the first input will be 1100, then the solving of this, then all of these three will get shifted in the second operation, something like this I already told. Then the NOR of this will be shifted like this and it will go on. So it is asking after 4 clock pulse. So it can ask for any number of clock pulse and you need to give the answer. It can ask for the period of the clock pulses, that whenever this particular input will come again will be the period. Then in the sequential part, there is one more topic which is flip-flop convergence that I have like that I spend a lot of time on. So you should be aware that how can we do the flip-flop conversion that can help you in certain questions to do a quick analysis of some of the questions. So this was more important topics from the sequential aspect. So is there any doubt in the sequential part? Please ask if you have any doubts from the sequential part. Is there any doubts? Okay, so and then we dive into the maybe we can go for maybe combination. So there were certain problems. So in the combinational part, if you remember, so the last combination part has a propagation delay question in which I guess there was a multiplexer and there were two parts and it was asking what can be the maximum propagation delay. So there are the types of question that again ask you that how the concept has been clear. So I am not sure, I'm not remember the exact question, but there were two multiplexer in series and there were I guess two different states, one with a knot, and it was asking what can be the maximum propagation delay of that particular circuit. So if the concepts are clear, that questions are very easy, and if they are not clear, then we'll never be able to solve them. So there was a question of this propagation delay. Then we what we had is not remembering. So again, some of the important topic are you should be aware how to make a K-map quickly, because K-map is required in each and every question basically. You should have a good understanding of Boolean algebra and so on. Like there are very basic properties such as a plus a complement b is a plus b. This is a consensus theorem. So if you don't know the basics, then that might result in not very good exam. So you should be aware of all these things. So if I wrap up this with certain different things, so we had these courses. This is a course outline. So I'm just marking one very important topics from each of the weeks. So in week one, wait, yeah. So in week one, we had this relation switching. So again, some of the diodes and transistors were defined in the week one lecture. So you should be aware how to, all of these things are working. Then there was noise margin concept. Again, there was CMOS logic concept, which was very easy. And in week two, I already told that you should be aware of the basic logic gates, the NAND or universality. So I told you, I guess, if you remember, that NAND node are universal and NAND implementation is good for AND or implementation and NOR implementation is good for OR and implementation like that. I told you that A, B plus C, D is easier to make with NAND. If you remember, then A plus B times C plus D is easier to make with NOR. And similarly, Boolean algebra is there, then K maps. I've already told you this is the important topic. Then this minimization is can be done using K-map, and then there are static hazards. So this is very easy topic. So you should have a good grasp that how can we find what is the type of hazard. Then there are circuits such as multiplexer. So multiplexer is the most important topic in the conventional part. Then we have encoders also, but I guess multiplexer is the most important topic. So week 5 was all about this number systems. So I hope that it is already clear that number systems is important and it is also very easy. Then at the end we have certain adders and magnitude comparator is again a very important topic. And then we can come to the sequential part in which what we have is we have this SRDK JK flip flop, SRD JK flip flop, which are you should know how to convert each of them into each other. Then we have analysis of different flip flops. Then we have registers, universal shift register that I've already said. Johnson counter is one of them. Ring counter is one of them. Then yeah, one more topic is the sequence detector. There can be state diagrams in which you need to detect the sequence. Then we have up and down counters. We have synchronous, asynchronous counters that I have already explained that what can be the questions. Again, Mealy and Moore model, I have already showed you what can be the types of question. And again, the final last week was all about DAC and ADCs. So I've also told you some of the important questions that I feel are important. And in today's week, we have already seen that most of them are memories and theoretical type of questions. So that might be easier. So these can be the important topics from the last, that is PLA and PL. There can be questions from these. So if you have any doubts now, particularly in the course, then you can ask. Otherwise, we can wrap up this course and all the best for your exams. And we can meet maybe with some other course in the next semester if you take so. So if you have any doubts, you can ask. Otherwise, we can wrap up quickly. Okay, fine. So I hope there are no doubts. Please confirm all of you that you have no doubts, and then we can wrap up the session. Is there any doubt, anyone? Okay, then. So all the best for your exams. Try to do it in a smart manner. Try to be good about your concepts, and all the best. I hope you will do well. Thank you, everyone. Yes, so you can contact anytime. So I have already provided my email ID. There is also NPTEL channel. Uh, so I'll type in the email ID again. So this is the email ID that you can contact on if you have any doubts. And there is a NPTEL channel. I guess you are already aware of that. So all of these videos are available in the NPTEL channel. You can search on YouTube this name, and then you'll get all the videos, and also all the PDFs are shared in the drive link that is given by NPTEL to all of you. So I hope it is clear. Yeah. So thank you, everyone. All the best again for your exams.